Hi, ladies and gentlemen. Note 6.8 are on rates of change in exponential and logarithmic functions. So question number 1 says the average number of students per computer in public schools is given in the table. Year 1 is 1983. So the first thing we need to do is calculate the average rate of change in students per computer during the entire time period. So let's do the entire time period first. It also asks us to do it during the first middle 5 years of the data, but we'll do the entire time period first. So for the entire time period, remember we have to do f of b minus f of a, and actually let's write a rock equals, because we're finding the average rate of change. So do f of b minus f of a all over b minus a. Okay, so here, when I look at my chart right here, if I want to do it over the entire period, a is 1, b is 13, because that's my input. This is f of a, and this is f of b. Okay, so here, when I do this, I'm going to have 10 minus 125 over 13 minus 1. So when I do this division here, I end up getting negative, or when I do this evaluation, I get negative 115 over 12, which is equal to, if I were to divide those two numbers, about 9.58. So I can say here that this is approximately equal to negative 9.58. So that means right here that we can say that the number of computers went down per student decreased by about what this is telling me is that the average rate of change in students per computer decreased by about 10 students per computer each year. Okay? All right, so now let's go ahead and do the middle 5 years right here. So we'll do middle 5 years. And if you look right here, the middle 5 years will end up being from year 5 to year 9. So these are our middle 5 years right here, because we've got 4 above and 4 below. So this is our A, this is our f of A, this is our new B, this is our new f of B. So to find our A rock, I'm going to use the same formula, but I'm going to do 18 minus 32 over 9 minus 5. So I end up getting, right here, this becomes negative 14 over 4. And if I were to divide negative 14 by 4, I get negative 3.5. So right here, we can say that the A rock in students per computer decreased by 3.5 students per computer each year. Okay, so now what can you conclude? Well, if you notice right here, the average rate of change for the entire time is higher than the average rate of change for our middle time that we have here. So it either means that the rate of change is steeper at the beginning or it's steeper at the end. And if you look right here, it's clear that it's steeper at the beginning because this right here is decreasing by more at the beginning than it does at the end. So therefore, we can see that this is going to be an exponential graph, but it's going to be exponential decay. Okay, so what we can say right here is the A rock was larger over the entire time period then over the middle 5 years, making making the rate of change larger either at the beginning or at the end. So clearly, when I take a look at this right here, we can say the data shows the AROC is largest during the first 4 years. Okay. All right, so now question 2 says to determine the instantaneous rate of change in students per computer for year 8. So in order to find the IROC right here, what I need to do is f of, here it's going to be at x equals 8. So I need to find f of 8.1 minus f of 8 all over 0.1. Okay, but I don't know, I don't have a function for what f of x actually is. So we're going to go to Desmos and we're going to get a regression to get a function for what f of x is. So if you take a look right here, I graphed it out on Desmos. I just created a table of values, and if you look right here, this is our graph, and it's clear that it looks like it's going to be exponential decay. Now, on Desmos, we can actually get an exponential regression. So we're going to say y1 is approximately equal to, now I want an exponential equation right here. So I'm going to say, I'm going to put approximately equal to here. And remember, A is my vertical stretch times B is my base, to the power of my horizontal stretch or compression, which is the reciprocal of k, times x minus d, where we've got our horizontal shifts. And then we also have our vertical shift. So this right here is going to give us all the values that we need. So if you look right here, it looks pretty good, but it levels off a little bit earlier than where we want it to level off, but that's okay. This is our regression. It's 0.9914, and we have all of our values. We've got A, K, C. We even have our base, our B right here, and our D right here. Okay, so what I'm going to do here is I'm going to type in f of x is equal to a times b to the power of k times x minus d. I keep typing 3, sorry, plus c. So what I want to do is, like we did here, I want to figure out what f of 8.1 is. So I'm going to say f of 8.1, and I get about 17.176 here. So I'm going to say this is approximately equal to 17.176. Now I want to find f of 8, and I get 17.319 all over 0.1. So now I want to subtract those values. So instead, what I'm going to do is I'm just going to actually type this all into Desmos exactly how I see it. So I get f of 8.1 minus f of 8 is negative 0.142 over 0.1 will give me approximately negative 1.42. But let's go ahead and write this out as over 0.1 right here, and we get negative 1.42. So we can say right here that at year 8, excuse me, right here, we can say that at year 8, the IROC in students per computer was decreasing by about 1.42 computers, or students, sorry, per computer. All right, number 3 says the graphs of y equals 10 to the power of x and y equals log base 10 of x are shown. Determine how the IROC and the y values for each function changes as x grows larger. So for our first one, we've got y equals 10 to the power of x. So we know that this is an exponential, and we know that it has a horizontal asymptote at y equals 0. And that means that for infinitely large negative values of x, y is getting closer and closer to 0. So if I want to look at the rate of change, if I'm looking at this right here, this is getting closer and closer to a horizontal line, which means that my rate of change is pretty much minimal until I get to a point where my graph starts to increase. And remember, the IROC is your slope of your tangent line. So if you notice, as we get farther and farther along, our slope is getting steeper and steeper. So we can say, one conclusion that we can make is, as x approaches negative infinity, the IROC is approaching 0 because it's getting closer and closer to a flat line. And then our second conclusion we can make is that as x is approaching infinity, our IROC is getting closer and closer to a vertical line. So our IROC is getting closer and closer to infinity, because remember, the slope of a vertical line is undefined because it's getting closer and closer to infinity. Okay, now for y equals log base 10 of x, we know that we have a vertical asymptote when x is equal to 0. So we know that right here, our IROC here is pretty large until we get farther and farther along on our graph, and then the slope of the tangent line is getting closer and closer to 0. So we can make two conclusions. We can say, as x is approaching 0, the IROC, as x is approaching 0 from the right side, the IROC is getting closer and closer to infinity because we've got a vertical line. And it's approaching 0 from the right side because from the left side it's undefined. And then we can say, as x is approaching infinity, the IROC is getting flatter and flatter and flatter, so the IROC is getting closer and closer to 0. And that's all we need to know for this type of a question. All right, that's it. Let me know if you have any questions, and I will see you later. Have a great day. Bye.